Hello, this is Anna Doulas with the second video of the Modulus beam optics of ECE 513 Intro to Optics and Photonics course. In this class, the learning objective is we're going to understand a little more about the features and behavior of Gaussian beams. We're going to see the behavior of the intensity distribution, that the power of the Gaussian beam is always constant. We're going to talk a little more about the behavior of the beam width, how we're going to define the depth of focus, what is the beam divergence, and then we're going to discuss the phase of the Gaussian beam and the Goody effect. And finally, we're going to see that we need some additional parameters to define a Gaussian beam when we compare with a plane or a spherical wavefront. So the Gaussian beams, they have a radial distribution that we went over before, and it's the absolute square modulus of the complex intensity. So all the phase go away, and the only thing that we have here is the original intensity of the Gaussian beam, the decay due to how the beam width increases, and then some variations along the x and y axis. So for every C-plane, we have here showing that the Gaussian beam follows a Gaussian function. It's always going to be maximum at the position of x and y equal to 0, and it's always going to decay through that one for every observation plane, for every value of c. So the maximum value, it also gets reduced because at the moment that the Gaussian beam increases, the maximum intensity is going to be reduced. But we always has a maximum peak and in decrease and the order of 1 over e squared at the radial distance. So talking a little more about how we define the Rayleigh range. Originally, we defined the Rayleigh range how was the distance with the beam width increase a square to the beam waist. Well, now we're gonna see that the Rayleigh range is the axial distance in which the maximum of the intensity decays by half of the value. And when we are really far away from the Rayleigh range, that's the moment where here the intensity follows an inverse square law. So that means that it's inversely proportional to the square of the c distance. So talking about the power. So power is the integrated intensity through all the axes. And the power of a Gaussian beam, it's always the same independently of the distance theta. So that means that it's completely a constant. The only thing that changes is the area that we need to observe. But if we enclose completely the Gaussian beam, we always gonna have the power, the same beam power, and the beam power is half of the intensity peak multiplied by the beam area. So the beam area is pi square of the beam width. That's something that is going to be useful moving forward, and we can always express the radial distribution of the Gaussian beam in terms of the power, if that's something that because we know that the power is going to be constant. So thinking about the power a little more, we always need to think that 86% of the total power is enclosed in a radius that is equal to the beam waist, and 99% of the power if in the radius is 1.5 the beam waist. So that's again some multi-choice questions is about how much power we are enclosing within the beam waist. So 68% of the power will be the answer. So the beam waist, so we already introduced the beam waist in the previous class because we were defining the Q parameter. So the beam waist was in terms of the imaginary part of the inverse of the Q parameter, and we were defining in terms of the Gaussian beam, the Gaussian waist, where we are, and the Rayleigh range, where the Rayleigh range and the beam waist, they are related. So we're gonna see that the beam width always increases with c, we define the Rayleigh range here in terms of the square 2 of the beam waist. The beam waist is the position where we have the smaller width of the Gaussian, so that's where we're gonna say that our spot is minimum, and therefore we're gonna assume that the light is in focus. Moving forward, the focal spot is gonna increase it, so that's gonna become out of focus. And the spot, even though we have here the spot radius, is gonna be 2 times the beam waist. So if we are really far away from the Rayleigh range, then our beam width is gonna linearly increases with the distance c, and we can define that proportionality is gonna be related with the beam divergence. So the beam divergence is just the ratio of the beam waist over the Rayleigh range, but knowing the relationship with the Rayleigh range and the beam waist, you can just say that is lambda over pi beam width. And kind of here is kind of related what we were saying about the power. 86% of the beam power is confined within our beam divergence cone. So if we have the beam divergence, we can put it in terms of beam waist over Rayleigh range or wavelength over pi beam width, but we can see that it's proportional to the wavelength and it's inversely proportional to the beam waist. So let's do this in class problem. Let's think about a little bit what we need, what kind of wavelength and beam waist we require to have a highly directional Gaussian beam. So a highly directional Gaussian beam, it's a Gaussian beam with a really small divergence angle. So remember, the divergence angle is linearly proportional to the wavelength and inversely proportional to the Gaussian beam. So if I need a really small beam divergence, I have to reduce. I have like 3 alternatives. One is using really small values of wavelength, like source wavelength, like violet or blue, or even more into the ultraviolet range. And I need to have really wide beam waist, so the beam waist needs to be high. Or we can have the combination of both of them, shorter wavelength and wide beam waist. But that's kind of required to having a small divergence angle, which is going to provide a high directional Gaussian beam. So we talk about the spot focus, and it's double to the Rayleigh range, but on the previous class, on class number 10, we were saying that the Gaussian beam within the Rayleigh range is considered planar, since the size of the beam width does not change too much. And really far away, we are considered it's spherical. So this planar region is what we call the depth of focus, which is twice the Rayleigh range. And we can see there that the depth of focus is going to be proportional to the area of the beam, and it's going to be inversely proportional to the wavelength. So if in the case of high directional Gaussian beams that we were saying that we want to have wavelengths that are too short, now if the wavelength is too short, the depth of focus is going to be too high. So it's kind of like it's going to be inversely the behavior of the depth of focus and the beam divergence. So last class we were also introducing for the first time the complex amplitude distribution, and we were saying that we have here the amplitude where we have a decay because the beam width, and then x and y also have a decay with the beam width, and then we have the phase term, where the phase terms we can think about the part about the propagation of a plane wave or paraboloidal wave, since Gaussian beam is a shifted paraboloidal wave, and then our first retardation. So the retardation phase is the inverse of the tangent of the transverse plane over the Rayleigh range, and as we can see here for the plot, there is a shift of pi, like the retardation is going to be equal to 0 for the waist position, but when we are moving from the right to the left, the same kind of like symmetrical position, they have a change of pi through the propagation of how the light changes through the propagation of the Gaussian beam. There is here a video of students kind of showing experimentally that change, and basically what you're gonna see is a contrast inversion. So the dark ring becomes bright and the bright rings become dark. That's the experimental confirmation of that change of pi. Just to finalize what I was promised, it was kind of to try to have an intuition about how many parameters we require to define a Gaussian beam. So if we were having a plane wave, we only need the amplitude and the direction of the plane wave. When we are having a spherical wave, we need to add an extra one, which is the origin, where it's placed, the spherical wave. But the Gaussian beam needs an additional parameter with respect to spherical. So we require the amplitude, direction, and origin, but we also need to know the beam waist or the Rayleigh range. So we require 4 parameters instead of 2 or 3. This is all the information for the class. See you soon.